Okay, so I wanted to talk about this problem that I'm attempting to solve, which is basically that if given a box that contains a particular configuration of elements, let us assume that these elements are charges, perhaps positive and negative charges constantly. So the output of the box represents the maximum amount of charges that are there. Basically the majority of the charges, which in this case would be negative, that would be the output of the box. What I am fascinated about is, given the output of the box, can we predict what the individual elements might have been? Here we will get 12 divisions, and can we predict what all of these 12 elements were given another box and given a machine that does not know what the initial states are? Can it just derive this from the box's output? So what we can understand from this is basically the box takes the majority. So it does not know the states that these objects are currently in, but it can do things on them. It can implement functions. Basically, it can maybe flip the state of the charge from positive down to negative. So if we assume positive as 1 and negative as 0, it can possibly bit flip the current bit that there is. And since the box represents the majority, given that it flips everything, the sign would be a plus. So if this is the algorithm I am using, how many possible steps can I minimize it to so that it can correctly output what the initial elements were? So my thought process is as such that if I have a 12 element grid and these 12 elements can occupy 2 of these states, so then I get 2 to the 12 power of possible combinations of what could be possibly this box. So this is an empty box which could have 2 raised to 12 states possibly, but what I saw is that if it flips the entire board, if it takes every positive and turns it into a negative and every negative and turns it into a positive, then what we get is the exact reverse. We would get a plus output from the box. So then, given a particular set of 12 states, its complement would be meaningless. So technically we only had to measure 12 to the power 2 divided by 2, which is 12 to the power of 11 states, which is still a big number. So given a particular grid, now I'm analyzing this. If I'm given a particular grid and I change its numbers, perhaps if it has a net sum of a 0, then it shouldn't, or basically since I'm counting positive and negative charges, if the charges in a particular grid are 0, then it shouldn't affect the state of the box. But if they are non-zero, supposedly in this one, then it might affect the state of the box. But will it? If I turn a minority into a majority, I might be able to get something out of it. But if I can do this and I realize that there is possibly no change, it could conclude either that the charges are 0 or that the majority charges are present elsewhere. So given this 3 by 3, 4 by 3 grid, if I change the second row to a minus, to a plus, minus, plus, plus, then the number of minuses goes to 1, 2, 3, 4, 5, and 6, and it equalizes it. 6 positives and 6 negatives, which would mean that the box also displays a net 0 as an output. But that only tells us that would actually tell us that there was a majority of negatives in this row. So, if I convert it into a recursive problem, then I essentially have this grid of 4 numbers that at first had a minus sign, but now it results in a positive. So it shifted towards the positive side. Hence, I can conclude that a majority of this array was a negative sign because it contributed to the function. And then when I do it individually for every single flip, perhaps if some other had a greater positive output, perhaps a plus 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 and a minus, then a minus 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 plus may result in a shift from 0 to a negative, hence implying that the majority is a positive. But we are not given shifts towards 0. We are only given whether it is a minus or a 0. If we were given weighted values, perhaps we might have found further use for this. But since we are only given a sign change, this algorithm might not always work. Or it might, but it needs further proof. So, looking at particular configurations, if I get a net 0 as an output, then perhaps in a bigger sample set, if it's still a 0, it would imply that this is a region of focus, but an example of 0 might not always be resultant from that, because if I take this row perhaps and flip it, it might become a minus, plus, and a plus, hence resulting in 1, 2, 3, 4, 5 pluses, but still the sign would be a minus. And if it's a minus sign, then I can conclude, I can't possibly structurally conclude. And if I take this one, it might become a plus, minus, minus, hence giving us 3 pluses, still implying that it is also a minus. The box's output would be minus in both of these cases, and yet that would not imply anything about the particular rows, since it contains still a minus. So, will I have to iterate through all 2 raised to 11 combinations? Well, in the best case scenario, everything else could possibly be unevenly distributed, and this would be a plus, and this rest might result in a minus, and the net output might be a 0. In that case, flipping the first bit would result in a minus, and that would give us a minus sign, and flipping everything else on the converse hand would give it a plus here, hence resulting in a plus sign. Hence, we might realize that this is the odd element, and that there are an even number of negative and positives here, except one that complements this. So a net 0 output would allow us to maybe look at a particular bit and identify it on a one-to-one basis using this algorithm. It takes the first bit, then flips it and looks at the sign it changed to, which would quite possibly be the sign that it's not. So if the initial state is 0, that would imply that the rest would sum up to a minus, and this one element, if it's a plus, flipping it would mean the box would give us a minus as an output. Hence, this would imply that the first bit is positive. Doing this for every other bit, we could do it in O of n times, means in linear time, but that is if the box's output was perfectly 0. But particularly if the box's output is negative, that would imply that if this is negative, then the entire box's output should also be negative if we construe the negative box value of this inner box. Then perhaps flipping it, if it results in a 0, we can imply that the bit was a minus, and if it's still, perhaps if it implied a minus, then this can't be a plus. So if it implies a minus, we can take the first element and then we can assume this as b of x, which is what the box's interior aspect should call. And yet the only output available to us is what the bigger box says. So if the bigger box says that it is a negative, and flipping it means a plus, and a b of x results in a 0, then a b of x is implied to also be negative. On the other hand, since it was a minus, if it changes to a plus, or perhaps since it was minus initially, changing this could imply 3 different outputs. Perhaps the minus becomes a plus, the minus becomes 0, or the minus stays a minus. So if the minus becomes a plus, then once we flip the bit, whatever we assume is to be a1 complement times b of x, or let's just say plus b of x is equal to positive, which would mean that both had to be positive. So this is a plus, this is also a plus, which says a lot about both the box and about this. If it is a plus, that means the initial state was a minus. If on the other hand, the minus stays a minus, then a1 complement plus b x results in a minus, which given two integers only, two charges only, would imply that both of them are negative, which would mean that it is negative, which would mean that a1 was actually positive. So I can do this approach for every single algorithm, and I'm afraid it's going to be wrong, but I can still try it out. And that's what I'm going to do. Thank you.